Okay, so thanks, and thanks Steve for doing a great introduction on reionization, so I don't have to say too much, but I'm going to be telling you about what we've been doing in the GLASS survey to try and understand reionization and even more of cosmic history. So reionization is, as Steve just told us, an incredibly important time in the universe's history. It's intrinsically linked to the formation of the first stars and galaxies. So if we want to understand the reionization process, we need to understand the first populations of stars and galaxies. With current observations, the ways that we can do this, I'm going to talk about two main probes. So the first is to understand the evolution of the galaxy population as a whole. So this is what we do with luminosity functions. So as Steve was saying about trying to understand, are there enough galaxies to reionize the universe? And secondly, using the spectroscopic properties of those galaxies to make constraints on the IGM itself. Okay, so when we look at luminosity functions and global evolution of the galaxy population, we find it's actually pretty easy to model and understand this evolution in luminosity functions when we consider that the growth of halos is the dominant driver of galaxy growth. So this is a model that I worked on last year with Michele Trenti and Tommaso Treu, and we found that when we made some very simple assumptions about what drives galaxy formation, so we assumed that star formation rates are basically proportional to the halo assembly rates, and then we assumed a fixed stellar mass to halo mass relation, which I think Richard will talk about in a bit later. So this is basically saying that there's no evolution in star formation efficiency, and we found that we could produce luminosity functions. So these lines are our model that matched with observations over 13 gigayears of cosmic time, which was I think we were slightly unexpected that it worked this well. But so all of these points are observations, and our model goes pretty much straight through them from redshift 0 to redshift 5, 6, 7, and then out to even higher redshift. And the nice thing about this is that we're seeing these clear circles here are data from the frontier fields where we're pushing right out to the very steepest end of this luminosity function, and these simple models still work remarkably well. And so this is something that really arises naturally in this model, these very steep faint end slopes that you get at high redshift, which is telling us that star formation is mostly occurring in small, low mass halos. And this also goes some way to explain the luminosity density evolution that we see. So a few years ago, there was people sort of freaking out that the luminosity density had suddenly dropped from redshift 8 to redshift 10. But again, this is very naturally explained in our model when you consider that we're only seeing the galaxies that are big enough to observe. There are lots of other galaxies. This red line shows sort of all galaxies in our model, but most of them are just too faint to be observed. We also explain this evolution in the luminosity density or the cosmic star formation history because as you go from higher redshift, you just have more galaxies forming. As halos become big enough to host galaxies, the luminosity density increases, and once they get to this point, they turn over because they have less fuel. They're not able to accrete any more dark matter or gas. Okay, so from models and from observations, we see that there are plenty of galaxies out redshift 7, 8, but detecting them and measuring their spectroscopic properties is incredibly challenging. So there are only 2 spectroscopic conformations of galaxies beyond redshift 8. Most of the time when we're looking for these galaxies spectroscopically, we're looking for Lyman alpha. And only one of those galaxies was detected with Lyman alpha. It's the Zitron object. Most of the time when you go and try to take spectra of these objects, you get spectra like this. This is my advisor Tommaso's perfect example of noise. So it can be a bit depressing, but hopefully we can try and learn things from the non-detections as well. And one of the things that we're seeing is that when we go from redshift 6 to redshift 8,